Okay, so let's see how we would actually use a cathode ray oscilloscope. On a cathode ray oscilloscope, the time base is not usually ever off. Okay, we always put the time base on and we have it to some sort of setting. So you can see here, we turn a little dial, and that dial at the minute is pointed to 50 milliseconds for each division. Now, there's usually very fixed amounts we can turn them to, and they're usually nice whole numbers. So you're not going to get like a, I don't know, 32.17 milliseconds per division. So usually like 50, 100, 5, whatever. Um, this really, what this does is it puts that sawtooth voltage across the horizontal deflection plates and cause it to sweep across the screen the dot sweep across the screen in a period of time. We don't need to worry too much about what's happening in the background there. All we need to know is really the x-axis on our cathode ray oscilloscope is time, and it has this scale based on our time-based setting. The Y sensitivity then takes an input voltage into our cathode ray oscilloscope, deflects a little beam up and down based on that, and this just tells us really the scale then in volts for our Y axis. And what we tend to use this for is to measure things about waves. So for instance, if I got a wave that looked something like this on my screen, okay, what I can tell from that is, well, our peak is 2 divisions up. Okay, so taking our Y sensitivity, we have 2 divisions. It's 10 millivolts per division, which means the peak voltage is 20 millivolts. Also looking at our waveform, from there to there is 10 divisions. Remember, our time base gives us our kind of scale on the x-axis, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 squares or 10 divisions along there. So that whole wave takes 10 squares, 10 divisions, but each division, our time base tells us, is 50 milliseconds. So the time period for that wave would be 500 milliseconds. Do be careful of the little unit in there. That could be milli, micro, or anything else really. From that then I could work out the frequency, because that's 0.5 seconds. So we do 1 divided by that, and we get that the frequency is 2 hertz. Now, quite often we get a lot more than one wave on that screen. Now I'll probably draw this really badly, but if I try and draw a few waves on here at once, like what I could try and do is measure the time period for one wave like that. I might get that it's what, 2.5 divisions, but better than doing that, and what they would expect you to do in an exam is, okay, go from here to here, take the whole thing. I haven't drawn that wave quite right, but I have 1 wave, 2 waves, 3 waves, 4 full waves there. Okay, and remember it's time, so really I have 4 time periods there, is equivalent to our 10 divisions. But that means that our 10 divisions, because of our time-based setting, which is 50 milliseconds, I'll just go down here to finish this off, means that 4 time periods is equal to 500 milliseconds. Therefore, the time for one wave would be, time period, would be 500 milliseconds divided by 4, which is 125 milliseconds. Okay. Try the example that's in your notes, and I'll put a little video at the end of that, just go through it.